Hello everyone, this is Dr. Pramod Kothmire. I belongs to School of Mechanical Engineering working as an associate professor. Welcome all to online course of computational fluid dynamic. Today's video lecture we will be seeing the convection diffusion equations which are useful for solving the problems which are related to heat transfer and fluid flow using computational techniques. So in this particular video lectures, we will be studying those equation and the discretization computational schemes, okay, where we can solve industry and research oriented problems which are related to convection diffusion. Okay, so let us first understand the schemes of CD equations, and before understanding these schemes, let us consider one physical problem. Okay, so let us consider one physical problem. Okay, so I'm considering one plate, flat plate, okay, which is heated, and we need to understand how the convection take place through this flat plate. Okay, so let us consider the wall of the flat plate is at TW, okay, which is greater than ambient temperature TA. Okay, so two temperatures I have defined over here, temperature of wall and temperature of air. Temperature of wall of flat plate is greater than temperature of air. Now on this flat plate there is a free flow of stream. Okay, this is a free flow of stream. Let us consider temperature of this free flow of stream as T infinity and velocity also at T infinity. Okay, so I am defining a physical problem. This is a flat plate. I am not much worried, at least now, with the geometry and the geometrical parameters, material properties. I am just defining two variables. One is the temperature and another one is the velocity. Okay, so the temperature of wall is TW, which is greater than ambient temperature, and the free flow of stream which is flowing over this flat plate is at temperature T infinity, and the velocity of fluid is U infinity. Okay, now please understand, on this flat plate, okay, or through this flat plate, how heat transfer will take place, that we need to understand. This mechanism we need to understand, transfer of heat. So everyone know that there are three mode of heat transfer. One is conduction, another one is convection, and third one is radiation. Okay, now among these three, how is the mode of heat transfer, how is the mechanism of transfer of heat through this flat plate, we need to understand. Okay, so one important concept here we will be learning, which we have not covered in our third year engineering heat transfer, that we will be seeing here in computational fluid dynamics. Now in computational fluid dynamics, when you are considering this as a flat plate and the wall boundary condition, okay, wall boundary condition, if we will consider on this flat plate, we will consider a very important wall boundary condition, that is no slip. Okay, so when there is a no slip boundary condition, in real practice, the very first layer which is to the wall, to the surface of the wall, which is strict to the surface of the wall, okay, this air layer, when it is subjected to no slip boundary condition, this air molecules, okay, this air molecules, or you can call it as air particles, okay, they are at velocity 0. Okay, these air particles, they are at rest. Okay, so when we say physically, a very next layer, a very first layer to the wall surface, Okay, these air particles, their velocity is zero. They are at rest. In computational language, we say that it is a no slip boundary condition. Okay, so no slip boundary condition, always del dot u is zero. Okay, now for this boundary condition, this velocity of particle is zero. Now hence this will act like a blanket. Okay, this entire first layer will act like a blanket of air particle. Okay, now in order to transfer the heat from the surface of the wall, this heat need to overcome this barrier. Okay, in order to have a transfer of heat from the surface of wall to ambient, they need to cross this barrier. Okay, so now since these air particles are at rest, they are acting like a blanket. Okay, we will consider it as a one single layer. We consider this blanket of air as partial solid. We consider it as a partial solid. So a very first layer, when the heat has to transfer a very first layer of particle which is near to the surface of the wall, here the mode of transfer is conduction. Okay, here the mode of transfer is conduction. Okay, now after this it has to transfer the heat by overcoming the barrier of this free flow of fluid. So here the bulk fluid is the fluid. Okay, bulk fluid is the air particles and they are in motion. Okay, so first layer there is a conduction and second layer there is a heat transfer because of this fluid particle, fluid particle, bulk fluid particles. Okay, so here the heat transfer will be called as advection. Okay, so here it is called as advection. So one is the conduction and another one is the advection. This all, okay, addition of this conduction heat transfer and advection heat transfer, okay, we call it as convection. We call it as convection. Okay, so in all together the convection is simply a sum of conduction and advection as far as this problem is concerned. Okay, so very first layer there is a conduction and the second layer there will be a advection. In all total will be the convection. Now please understand, here basically we will be highlighting on what? Transport. Okay, we are highlighting on transport. So we either transport mass, okay, through this physical phenomena, or there is a transport of momentum, or there is a transport of energy. Okay, there is a transport of energy. Now if you are focusing on conduction, okay, for conduction we have the governing equation as what? Fourier's law. We have governing equation as Fourier's law of conduction. Okay, this is Fourier's law of conduction. Now in Fourier's law of conduction, Q is the transfer, is the important parameter, transport of heat. Okay, and it is always proportional to temperature gradient, negative of temperature gradient. Okay, this is proportional to negative of temperature. Now analogous to this physical equation we have fixed law of diffusion. We have fixed law of diffusion. We have fixed law of diffusion. In fixed law of diffusion there is a transfer of mass. Here there is a transfer of heat. Okay, analogous to heat, analogous to this equation, we have fixed law of diffusion where there is a transport of mass and there it is proportional to concentration minus dc by dx, concentration gradient. Okay, now since these both are analogous, okay, here in the first case there is a transfer of heat and since transfer of heat is analogous to transfer of mass, we call this particular term as diffusion. Okay, we call this particular term as diffusion. So diffusion plus advection will be your convection. Okay, so convection is not merely advection or not, it is purely a conduction, but it is a combination of diffusion and advection. Okay, so the most important task is, okay, let me make clear, the most important task is to study the frame, okay, framework, okay, to study the framework, okay, to study the framework is the most important task. So we have the framework for solving this equation. Okay, we have heat transfer as the framework. We have, because there is a transfer of heat, Q, okay, conduction. Then conduction is nothing but diffusion, and diffusion is analogous to mass transfer. So we have mass transfer as well as we have momentum transfer. Okay, we have momentum transfer. Okay, so merely this convection diffusion equations, they are mass and momentum equation. Okay, we need to solve mass equation, that is continued equation, and Navier-Stokes equation, okay, to get the solution for the problems which are belonging to convection diffusion CFD oriented. Okay, so we have this framework: heat transfer, mass transfer, and momentum transfer. But in this particular chapter we will be focusing on heat transfer and mass transfer. Momentum transfer can also be used to solve convection diffusion problem, but they will be considered as the different framework. They will not be considered under this framework. Okay, now there are two reasons for this. Okay, now thou convection diffusion is having heat transfer, mass transfer, and momentum transfer, but heat and mass transfer will be considered as different framework, and momentum transfer will be considered as different framework. The reason for this is there are two reasons. Okay, the first reason is in heat transfer and mass transfer we will be consider temperature as linear and velocity as a single variable, different variable. Okay, velocity as a single different variable in heat transfer. Okay, whereas in momentum transfer you have the variable like this: u dot u, v dot u dot w. Okay, where u is what? Velocity component in x direction, v is velocity component in y direction, and w is velocity component. We have the product of u dot u or v dot u or u dot. This makes the equation non-linear for a momentum transfer. Whereas for heat transfer we have temperature as a linear parameter and velocity as a separate single variable. So equation is linear here, and here it is non-linear. Okay, so you need to have a special iterative techniques in CFD to solve this momentum transfer so as to observe its non-linearity. Okay, so linear equations can be easily solved, and we have a certain equations derived from this convection diffusion equations, but same cannot be used for momentum transfer. We need to have the separate advanced iterative techniques, special techniques of iteration, okay, to solve this momentum transfer so that we can absorb the non-linearity which is present because of these terms. Okay, okay, so this is the first reason. Second reason is the source term. Okay, the source term momentum transfer is related to pressure. Okay, there is a pressure gradient, and explicitly we need to have the, we don't have the equations for solving the pressure gradient. Okay, so here that is not the case. In heat transfer we don't have the pressure gradient. In momentum we have that pressure gradient terms. Okay, so these are the two reasons why momentum transfer will be considered as a separate framework. Okay, it is not considering heat and mass transfer. So throughout the chapter I will be focusing on heat transfer and the linearity of the equation. so that we can get the set of equations, and we will be studying several schemes like central differential schemes, then exponential scheme, hybrid scheme, power law schemes, upwind schemes. Okay, the advantages and limitations of previous scheme over the new one in the upcoming lecture.